So starting off with video 2 for our weather water final, we're going to move on to some of these other topics further down here on the checklist. So with this, we're going to start with water in the air. We're going to look at condensation, evaporation, humidity, dew point. One of the first things we're going to say is with water in the air, we look at the dew that's left behind. So we have whether it's a mirror in your bathroom after you take a shower and you get that fog left on the mirror, or the sweat from a soda can on a hot summer day. The reason these things happen is we have warm air that could hold a lot more moisture. As it cools, when it comes into contact with the cold soda can or the cooler mirror, it then can't hold on to all that moisture, and it has to leave that dew or that water vapor, or that little bit of liquid behind. And as it leaves that little bit of liquid behind on the mirror and on the soda can, that's that sweat or that dew drops or fog and haze that we see on the bathroom mirror. That cooler air can't hold all that water vapor, and it leaves it behind on that surface. We see the same thing happen with, a similar thing happen with evaporation, where we have a puddle of water, and as that puddle of water gets heated up by the sun and by the air, it then gets the water excited, and that water is going to change from a liquid into a vapor or into a gas form. So that's talking about their evaporation and condensation. So when we have condensation taking place, that's our examples of the liquid being left behind on a soda can or on a mirror. And when we have a puddle that dries, or a drop of water that dries on a surface or evaporates away, those are examples of water changing phase or changing form. So with condensation, we're looking at water going from a gas back to a liquid. And when we're looking at evaporation, we're looking at a liquid changing into a gas. So this kind of brings us in a little bit to even the water cycle and how we get clouds forming and a whole bunch of different processes. Even with humidity. Humidity is going to be the measure of how much water vapor is in the air. Okay, and we talk about the air being saturated. The air gets saturated at a certain temperature. Like we were using the examples with the dew forming on a mirror. Air can only hold so much water vapor, and at different temperatures, that amount of water vapor goes down. So as the air cools, it can't hold on to all that extra water vapor, and it has to release it. So when we kind of look at the dew point is going to be the temperature at which the air can no longer hold that water vapor and has to either get rid of some, or it just has to stay at that temperature, saturated full, and can't get any more water vapor. We also looked at relative humidity and calculating what the relative humidity is. So we kind of, in these situations, look at how much water vapor is in the air compared to how much water vapor the air can hold. And then we turn that into a percent. And when we do that, we're looking to see, what the percent of relative humidity is. On a normal day in the summertime for Pennsylvania, we're looking at usually very high humid days, where we're looking at like 80, sometimes even 90% relative humidities, where it's very, very sticky and muggy. So we would see the relative humidity being very, very high. On winter days, we see very dry air, so our relative humidity would be very low. We're looking at 20% or less. So there's not a lot of water vapor in the air compared to how much it can hold. So that's kind of how we see humidity and relative humidity and dew point. Humidity, the amount of water vapor that's in the air. The relative humidity is the percent of water vapor in the air. And the dew point is the temperature at which the air gets filled with water vapor. Then we look at how clouds form. So we start to look at rising warm air, and rising warm air is going to lead to tend to have a lot of water vapor in it. And as it has that extra water vapor in it, it's going to rise, and as it goes up through the atmosphere, it's going to cool off by about 5.5 degrees Fahrenheit every 1,000 feet or so. It goes up. Eventually, it's going to cool to the dew point, and when it does that, that's when condensation is going to start taking place. And those water droplets are going to stick to what we call a condensation nuclei, and that's like a little surface, whether it's a piece of dust, piece of pollen, some smoke. In class we made a cloud in a bottle where we had put a little smoke from a match inside a bottle, and as we put a little water in there, it squeezed the bottle to heat it up and then let the bottle go, and as it cooled, it condensed and it kind of stuck to the smoke that was left over from the match, and we got a cloud forming in a bottle. And that transitions us into talking about some fresh water and a little bit of the water cycle. When we look at types of fresh water, we're looking at things like clouds, frost, glaciers, groundwater, lakes, rainwater, rivers. There are a lot of different examples of fresh water. Really, when we're looking at fresh water, we're not talking about being polluted or being clean. We're talking about if it has salt in it or not. So we're looking at that salty ocean water versus fresh water where it's not having any salt in it. So even though 97% of the water on Earth is ocean salty water, there are a lot more examples of fresh water, but they only make up the 3%. And of that 3%, a lot of it is frozen in ice caps and glaciers. As we talk about the water cycle, we're talking about evaporation, condensation, precipitation, all of these different things that we've gone over and you've gone over in other classes, even in elementary school. We're looking at the water cycle as just how water moves from one place to another on the surface of the Earth. And that then brings us into some other topics where we start to look at how wind moves. Okay, and we talk about wind always moving from areas of high pressure to areas of low pressure. And we talk about local winds. With local winds, we're looking at, again, differential heating. And we're talking about how land heats up faster, water heats up slower. And we have two types of local winds that we're going to focus on for this final. That's going to be land breezes and sea breezes. With land breezes, we're looking at nighttime, where land cools off faster and the ocean or the sea is going to stay warmer. So we're going to have warm air rising over the water, and then it's going to cool and sink over the land, and we're going to have the wind at the surface of the Earth move from the cooler land towards the warmer water. And where the cooler land is, that's that cool, heavy, sinking air. That's going to be our high pressure area. And over the water, where it's warm and lighter and less dense and it's rising, that's going to be our low pressure area. So that wind's going to again move from high pressure to low pressure, from, in the land breeze case, from the land to the water. We're always going to name these breezes by where they start. Okay, so in this case, land breeze, the wind moves from the land to the water. The opposite of that is during the daytime we would have a sea breeze. A sea breeze is going to be when we have the land heating up more than the water, because during the day land is going to take less energy to heat up than the water, and that goes back to that again idea of differential heating. So as that land heats up, we have warm air rising over the land. It then cools and sinks down over the water or sea, and we have then at the surface the air moving from the sea to the land. And with the sea breeze, we're going to have high pressure over the water and low pressure over the land, and again wind moving from areas of high pressure to areas of low pressure. So that sea breeze has the wind moving from the sea to the land. And that's our kind of differences there with the different types of local winds and how the air moves from areas of high pressure again to areas of low pressure. Okay, and we look at that differential heating as what causes the wind to move. From that, we can then start to look at different types of air masses. Air masses, when we start to talk about warm fronts and cold fronts, are very important, because the combining of warm air and cold air is what's going to give us these fronts or these different storms that are going to move through as we start to talk about thunder and lightning and trying to predict what's going to happen. Are we going to have stormy, cloudy weather? Are we going to have clear, dry weather? How severe storms are going to be. So we look at an air mass as a body of air with the same temperature and moisture. So warm air generally going to be lighter, less dense, warmer, moister. We look at cold air as cooler, heavier, denser, and drier as well. And when we have something like a cold front, we're looking at the cold air being stronger and doing the pushing. And it's pushing that warm air out of the way. The front is also going to be a little bit more vertical in shape. It's going to have more of a curve to it. We're going to see more cumulonimbus clouds associated with a cold front, and more severe weather associated with the cold front, more thunder and lightning. and stronger winds associated with that. These fronts are always named by whatever air mass is doing the pushing. So with the cold front, the cold air is stronger, it's pushing the warm air out of the way, so it is going to then be the cold front. With a warm front, these are larger fronts. They don't take place quite as quickly as the cold front, which is why the weather isn't as severe, because it's a slower, more gradual change. With the warm front, the warm air is stronger and it's pushing the cold air out of the way, and it's more of a gradual slope of a change. It's more of a triangle, straight line of change when you're seeing the clouds. We're not getting cumulonimbus clouds. We're going to be getting rain, but it's going to be a slow, steady rain over the course of many hours or two a day, where with a cold front it's severe, usually quick changes that take place in a few hours rather than a day or two. So that's kind of our big differences there between our cold fronts and warm fronts. And again, whatever air mass is doing the pushing, that's the type of front it is. Then we kind of start to talk about thunder and lightning. With thunder and lightning, starting with the lightning, we need to get separation of charged particles. So when we get that separation of charged particles happening in a cloud, that's going to be happening because we're going to get updrafts of air, and we're going to get different ice crystals and hail and rain moving inside the cloud, and it's going to push around some of these charged particles, giving us a usually negatively charged base of a cloud and a positively charged top of a cloud. And then we start to get the opposite charge happening at the surface of the Earth. Kind of like static electricity. We need that separation of charged particles where you start to move across and you go to touch the doorknob, and the separation or the difference in charged particles between your hand and the doorknob creates a static shock. That's what we're looking at with lightning. With lightning, we get these what we call step leaders coming down from the base of clouds towards the Earth, and we get these streamers that are kind of then reaching up off of the Earth back towards the clouds. And when these streamers and step leaders meet, that's going to then create a pathway for what we call the return stroke, or the bolt of lightning. And that return stroke or bolt of lightning is always going to go from the ground back up to the cloud. Now, that's when we have cloud-to-ground lightning. There are other types of lightning. We could have in-cloud lightning, cloud-to-cloud lightning, and cloud-to-air lightning. But for cloud-to-ground lightning, which is what we focused on in class and what our test is going to focus on, we always have that return stroke or bolt of lightning going from the ground back up to the clouds. So we have those step leaders coming down from the base of clouds, going towards the Earth, and the streamers coming up off the Earth, and they make a pathway for the lightning bolt to travel through, that return stroke, and that goes from the ground back up. And with lightning, we also have thunder associated with that. So because we get this static electric shock and this extreme heating of the gases from that giant flash of light, it's really going to heat up the air around that bolt of lightning to extreme temperatures. And when that happens, it's going to create a sonic boom. It's going to be a rapid expansion of the air molecules. Like we talked about before, as we heat up air, it's going to want to expand and kind of spread out a little bit. Well, with lightning, it's going to expand and heat up 5 times stronger than the surface of the sun, or 5 times hotter than the surface of the sun. So that's going to cause those air molecules to expand very, very fast, and that's why it's going to create a sonic boom and a shock wave coming off of that bolt of lightning. We're going to look at some weather maps on our exam as well. And when we look at the weather maps, we're going to again look for areas of high and low pressure, and we're going to want to see where wind is moving from areas of high pressure to areas of low pressure. And with these types of questions, we're going to look at the examples where we have the air pressure on the map, and we look for, again, the wind moving from areas of high pressure to low pressure. When we look at weather, we look at types of high pressure as being clear, dry, generally sunny weather, because we're not getting clouds forming from sinking air. When we have low pressure, we're looking at warm air rising, and that's what's going to get us clouds. So that's going to give us generally more cloudy weather and more storms with low pressure. The last thing that we looked at were climate change and greenhouse effect. Greenhouse effect is how the sun shines down onto the Earth, transferring energy there, and these gases are going to trap energy like a blanket around the Earth. And some of the problems we run into with climate change are increased temperatures, more health risks, animals going extinct, sea level rising, causing floods, and more severe